All right, 3.6, last section of material in chapter 3 that we're going to do for this test anyway. And this is called an overview of curve sketching. Now here's the good news. You have a calculator, at least most of you do, and you're allowed to use it on the test. So you can confirm the things that you are doing in this section with your calculator. Here's the negative. It means that if I don't see work to support it, it doesn't really matter if you can draw me a beautiful sketch off of your calculator screen. I'm not interested in what your calculator can do for you. I'm just interested that you can use your calculator to confirm. Okay? So everything that you do on the problems like these have to be shown out longhand. All good? Okay, let's take a look. So there are some important features inside of a graph that we need to be able to identify and then use to sketch it. And these are them. The first one is to determine domain and range. So do we have only positive values? Am I allowed to have negative values? Can I not have x equals 3? Those kinds of things. Okay, domain and range. The second one, intercepts, asymptotes, and symmetry. Intercepts, right, x-intercept, y-intercept, right? We find those, that's an algebra issue. We let x equal 0, y equals 0 for those. Asymptotes, we just talked about horizontal asymptotes in the last section, and in chapter 1 we talked about vertical asymptotes. So we've discussed both of those. And then symmetry we haven't discussed. We won't spend a lot of time on symmetry, but there are graphs that have symmetry that are very helpful. For example, y equal x squared, right? The left-hand side, the right-hand side, they're symmetric. If you knew what the left-hand side looked like and you knew that it had symmetry, you'd automatically get the right-hand side and vice versa. And then the new part that's definitely calculus and not something you would have ever seen in any previous class is the part on number 3. Locating values for which f prime of x and f double prime of x are either 0 or do not exist. So those are locations where we potentially have relative maxes and mins. We could also have an asymptote, though we would have already found it back on step 2. And then, or we could have inflection points. That's the other thing that we could have if the second derivative is equal to 0. So places where we have inflection points. And then determining, like it says, relative extrema, points of inflection in particular. Okay, so I think we can do one example, and we'll do our second example next time. The second example is much briefer, if I remember right. Okay, here's our example. We have f of x equals x minus 4 over x cubed. The directions say to analyze and sketch the graph of the function, label any intercepts, relative extrema, points of inflection, and asymptotes. We're actually going to go through all these steps. Sometimes you're asked to do all of them. Sometimes you get to skip over certain pieces, but we're just going to make it very comprehensive so that when you are given a function and an example on WebAssign or in your test or whatever, you've had experience doing all of the pieces you might be asked to do. All right, so our function is x minus 4 over x cubed. And we're going to start with the domain and the range. Okay, so looking at x values is domain. So domain, remember, is x values. Are there any x values that I'm not allowed to have? It's often easier to ask it that way. In this function. 0. Yeah, x can't be 0, right? So perhaps you're able to write this as simply that x cannot equal 0. Or maybe you're supposed to write it in interval notation, so you write it as negative infinity to 0, union 0 to infinity. A couple of different ways, right? All right. This is a rational function. And this rational function means that it is going to have potentially at least a horizontal asymptote, right? There might be a place where I actually can't equal a y value. Range is easier to do later than it is to do now. So I'm going to leave range blank, and if I forget to come back, somebody's going to remind me, hey, Dr. Hans, we forgot to do range. Doing it right now is not always the easiest place to do it. So we'll come back to the range. All right, so we're going to do intercepts as our next step. So intercepts are places where x or y, depending, equals 0. So if we want the x-intercept, we let y equal 0. So y equals 0 would look like this. And the only way that's going to happen, that is, that I'm going to get 0 out of this entire function, is if the top is equal to 0. The denominator cannot contribute to that, right? So when will the top of this equation equal 0? Yeah, at x equal 4. So this happens, I'll just do it right here, at x equal 4. So my x-intercept is at x equal 4, y equals 0. Now, if you want, I can't remember if I have a screen. I do. We're going to plot a few of these things as we go. So you can just sketch in a graph for yourself. Probably going to have to move mine a little bit. It says I have an x-intercept at 4, 0. So I'm going to plot, oh my goodness. Let's try that again. I'm going to plot that x-intercept at 4, 0, and I'll use blue. So it would look like that. Is that okay? 4, 0? Excellent. All right, y-intercept. So my y-intercept is found by letting x equal 0. And what do you notice if you try to do that? What is it? It doesn't exist, right? I get a 0 in the denominator, so there is no y-intercept. So I will not cross on the y-axis. And that makes sense because we already said that our domain did not include x equals 0, which would be the y-axis. So those two pieces are matching up. They should match up, and they do. Symmetry. So I told you we weren't going to do a whole lot with symmetry, but we'll talk real quick about it. This one, symmetry-wise, it doesn't have like a left-right symmetry, right? That's called even. The reason we know it doesn't is because I've already plotted a point over here at 4, and I didn't plot one at -4. Agreed? It also doesn't have what we would call origin symmetry. So origin symmetry has the ability to sort of rotate it 180 degrees around the origin. And if I did that again, I would take my value that's at 4, and it would rotate over here to -4. So there's no symmetry in this graph. If you think about it from an equation standpoint, it kind of makes sense as well. There's no symmetry because the numerator, x minus 4, does not have the ability, like x squared does, to have the same value if you put a positive and a negative in. Right? The left-hand side, the right-hand side. It doesn't work. So there is no symmetry. And if you wanted to wait to answer that question, kind of like my range question, until after you'd graphed it, you could do that too. If you were like, I'm not really seeing how do I make that decision. After it's graphed, you're going to very clearly see whether there's symmetry or not. So you could hold off on making that decision right now. All right, step 3 is the long step because it involves derivatives and second derivatives. And it's derivatives and second derivatives of a rational function, which means I'm going to use what rule to find my derivative? Somebody said it. Quotient rule. If you don't want to use quotient rule, you could do some algebra simplification. That would be another option, okay? I'm going to go ahead and use the quotient rule this time. And so this is step 3, and we're going to take the derivative of our function. All right, so we've got the denominator first, times the derivative of the numerator, which is 1, minus the numerator, x minus 4, times the derivative of the denominator, which is 3x squared, and divided by the denominator squared, which is x to the 6th. Is that all right? Okay. Anytime we're taking a second derivative, we really want to clean that first derivative up as much as we can because it'll make the second derivative process easier. So we're definitely going to want to do that, even if we weren't trying to evaluate this at 0, which we are. So I have x cubed. We have minus 3x cubed, and then plus 4x squared, all over x to the 6th. Is that all right? Yes?
Wouldn't it be 12x squared because 34?
So this gets multiplied here and multiplied here. So you want the 12 here. I see what you're saying. Yes. Looking to see if I have it written down, and I didn't. I've skipped some of my steps in my notes. Thank you. 12x squared. Okay, anything else? All right. So the first two combine. This would be negative 2x cubed and positive 12x squared over x to the 6th. Could you see anything that we could reduce, simplify, clean up at all?
Take it, 2x, x squared out.
Okay, yeah, so we have power of x here that's x cubed, this one's x squared, and this one's x to the sixth. So they all have at least an x squared in them, right? So we could reduce them by each dividing each of them by an x squared. So yes, we could rewrite this as -2, and it would be -2x, and then positive 12 over x to the fourth. Now there's two options. We either have it equal to 0 or equal to does not exist. That's how we would find relative extrema. We know what happens when the denominator here equals 0, that is the does not exist point. I have an asymptote. Now that might mean that the concavity changes, the increasing, decreasing changes depending on which piece I'm looking at. But we know what's actually happening at that location. It's an asymptote. The numerator, however, does give us a location where x is equal to 0. Where does x equal 0 in the numerator? Or not x equals 0, the function equals 0 of the numerator. 6. And the denominator, of course, is at x equals 0, but we get an asymptote there. All right, so what do we do with that? Well, we do a sign chart. This is the stuff we were doing 2 sections ago, right, in 3.4 and 3.3. This part of it's 3.3, I think. So we create a sign chart, and we put those values, namely 0 and 6, on our sign chart. Because what we want to know is the graph increasing? Is the graph decreasing? And do I have maxes or mins? So I use our derivative. You can use any version of it. We might as well use the final one because it's cleaner. And we're plugging in the numbers before 0, between 0 and 6, and then after 6. So what's the number before 0 that I could use? -1. Between 0 and 6. And after 6, 7. Remember, you can use anything you'd like. It doesn't matter. And we want to know what happens to the sign when I plug these in. And notice right here, if I plug any of them into the denominator, it's positive, right? Yes? So don't really care about the denominator. It's not going to change any signs. It's only going to be the numerator that does. So if you wanted in your calculator just to put the numerator in to make the decision, you could. Right? Or you can do it just in your head too. So if I put in -1 into -2x plus 12, do I get a positive or negative? It's positive. How about a positive 1? Also positive, right? And if I put in a 7, it's negative. And what we discussed about this meaning in section 3.3 is that means that this is increasing, and this one is decreasing. And in terms of drawing that out, sorry, my graph's getting really cluttered at this point. It would be like that. And what would happen right here? I have a max. So I have a max at 6 something. How do I find the y value corresponding to that? Back in the original function. So if I take my original function and I put in 6, 6 minus 4 gives me 2 over 6 cubed. What's 6 cubed? What is 6 cubed? I don't know. I don't have it written down. Maybe I do. Oh, I don't. What is 6 cubed?
216.
216. And if I were to simplify this, I'd get 1 over 108, right? That is the y value for my maximum point. 1 over 108. It's awfully tight in there. I want to pause for a second and I want to plot these things on my graph, okay? I never plotted the asymptote, so I'm going to actually start with that. There is an asymptote right here. That's not what I wanted to do. That is. Can you see the red dotted there a little bit? Okay, there's an asymptote there. I've got a point 6, and it's 1 over 108, which is very tiny and very hard to plot. Agreed? It's almost 0. So our best estimation is all we're going to go with, and it means it's going to be slightly above the axis. It's going to be really tiny right there. I also know my graph is increasing and decreasing in certain places. I know it's increasing before 0, right? That's what it said over here at the bottom. It's supposed to be increasing. So the graph is supposed to be increasing over here somewhere. Yeah? And the graph over here is supposed to be increasing until I get to that little tiny blue dot. And then after the tiny blue dot, it's supposed to be decreasing. But there's some asymptotes, and in particular, there's one asymptote that I didn't find. Let's find that asymptote, and then we'll pick back up with the rest of the problem there next time. This graph had a vertical asymptote. It was at x equals 0. It also has a horizontal asymptote. Thinking from college algebra, or from the limit stuff that we did back in 3.5, what is the horizontal asymptote that occurs on this graph? It's a little bit funny. I don't mean like funny like ha-ha, I mean like it's a little weird. What's the degree on top? 1. What's the degree on bottom? 3. What happens when the degree on top is smaller than the degree on bottom? Horizontal asymptote, but at what value? At 0. There is a horizontal asymptote. So I have a horizontal asymptote. I already did a vertical asymptote. I didn't write it down. I could do that. Vertical asymptote at x equals 0. There's a horizontal asymptote at y equals 0 here because the degree on top is smaller than the degree on bottom. Why do I say that's a little bit funny? Because you actually have an x-intercept and you have a horizontal asymptote, and they're both like that. That shouldn't happen, right? Like something weird is going on. So I will leave you in suspense until Wednesday, and we will come back to discuss why in the world that can happen, okay?